Today we're going to continue our graphing conversation, and we're going to talk today about parent functions and transformations. We've done a little bit of this already with our absolute value graph, but we're going to extend it to many more graphs as we move on. So what a parent function is, it's a function at their most basic state. In other words, the absolute value, we've already done some things with that. We've had a slope in there, we've had an h and a k. We found the h and the k move the vertex of the absolute value. But the parent function of the absolute value is just the absolute value of x. And that we know has a pattern or an xy chart, if you will, that if I plug in a -2 and a -1, a 0, 1, and a 2, I get out 2, 1, 0, 1, 2. If I were to graph the parent function, it looks real similar to a V, like so. So now we're going to do the same for a quadratic or an x squared function. We know that the parent function on this graph is y equals x squared, and it has a pattern or an xy chart of -2, -1, 0, 1, 2. And when I plug in a -2, I get out a 4, 1, 0, 1, 4. And if I graph this, you'll notice this rises much quicker than the absolute value, but it looks like a parabola, which we studied our freshman year. In our next example, you'll see that we have an addition of some number in front of the x squared. X squared is still our parent function, and it still has a general pattern of -2, -1, 0, 1, 2, yielding 4, 1, 0, 1, 4. But in order to plot the appropriate points here, what I'd have to do is I'd have to multiply all my outcomes from the original pattern by 2. So I'm going to take and multiply all these guys by a value of 2, thus giving me 8, 2, 0, 2, 8. When I graph this, you'll notice the shape of this graph is much steeper than the original y equals x squared. This has actually stretched the graph. Let's look at another example. In this case, same parent function, x squared. Pattern for an x squared graph is, again, -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. But in this case, after we're done plugging into x squared, we have to multiply by -3. When I multiply these values by -3, I get -12, -3, 0, -3, -12. So you'll notice in this case, if I graph these points, -2, -12, it's way down here. 1, -3, -1, -3. I get also a much steeper graph. However, not only is this stretched, but it's also reflected over x-axis. And this negative had something to do with that, because I'm taking all my y values, which were positive, and now I'm making them negative by multiplying by a -3. So here's some general truisms about any kind of graph. any kind of graph, and this is super important, any kind of graph can be written in this form. Y equals A times f of x minus h over b plus k. Now, f refers to the function. And that function could be like an absolute value, could be like an x squared, could be like a square root, could be x cubed, could be almost anything. All right? But when we express it this way, these variables all have something to add to the original parent function. H, just like in our absolute value, is a horizontal translation, and it moves everything left or right. Notice the H follows the subtraction in a similar way that it did in our absolute value. K deals with vertical translations, moving the graph up and down, and you'll notice just like in the absolute value, K is after a plus sign and it's outside of the function. Notice this is within a function, this is outside the function. A vertical stretch, we talked about this, or a Y multiplier, is also called dilation, all right? And that makes the graph either leaner, taller, or shorter, if you will, depending on its value. If the absolute value of A is greater than 1, then the graph's going to narrow. It's going to get leaner, if you will. If the absolute value of A is between 0 and 1, the graph gets kind of pushed down. It gets squished or widens. And then like we just talked about, if the A value is a negative, it's going to reflect points over that x-axis. Now this B term we haven't really used yet, but we will do so. And it's called a horizontal stretch, or an x multiplier. And if B is greater than 1, it's going to make the graph wider. It's going to open it up more. If it's between 1 and 0, it's going to narrow the graph more. And if it's negative, it's going to reflect points over the y-axis. Real important to note all that. So let's do some examples. My hope is that we never have to plug points in again to graph this. I mean, we could plug in 1, 2, 3, 4 in this graph, but that's painful because we have to do a lot of calculations. What I want to do is identify the parent function, which is x squared, identify its pattern, which we already know x squared has a pattern of -2, -1, 0, 1, 2, giving me 4, 1, 0, 1, and 4. And now I want to take a look at this equation. I notice that within the function to the squared, I have an h value, but h needs to follow a subtraction sign. So my h value would have to be a -1. My k value would have to be a 4. Now, if I move, because I know this is a translation to the left of 1, and this is a translation up 4, and I know my 0, 0 point has been moved by this translation, I'm going to go back 1, up 4. What I'm going to do is I'm going to put a little crosshair right here telling me that this is my new origin. And I'm claiming that my graph is not going to change at all because it hasn't gotten narrower and it hasn't gotten wider because there's no a value. Therefore, since my graph isn't changing, it still has this pattern. And I can graph this pattern from my new origin and have the perfect graph of this function. Let's do that. Let's go over 1, up 1, over 2, up 4, and plot these points. Notice, I haven't plugged into the original equation at all, but I'm claiming that this graph right here is an accurate graph of the function to the left. And to check this, I'm going to pick a point on this graph. This point right here is 0, 5. And if I've graphed it correctly, 0, 5 is a solution to this equation. So I would say 5 equals 0 plus 1 squared plus 4. 1 squared is 1 plus 4 is equal to 5. 5 equals 5. It checks. This graph must be right, and I have not picked a single point to plug into this to get the y value out. Let's do another example. Parent function once again is an x squared graph. Pattern once again, -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. Notice this is kind of set up the same way. This is the function. This is inside the function. This must have to do with the h value, but h follows the subtraction sign. So I change the look of the original equation first. I identify my h value to be -5, my k value to equal -1. There is, well, you don't see an a and a b. They can't be 0 because then the equation would equal 0. So a is equal to 1, b is equal to 1. That means there's no change to my x squared graph. It doesn't stretch vertically or horizontally. So what I'm going to do is I'm going to use my translation of back 5 and down 1 to plot this new origin. And then I'm going to state that my graph is not going to change from x squared because it hasn't stretched at all. So it's going to fit the same pattern. Therefore, if I were to take and go over 1 up 1 on both sides and over 2 up 4 on both sides, I'm claiming that this is an accurate graph of the function to the left, and I have not plugged anything into this at all. To check once again, I'm going to take a point. This point right here is -3 and 3. And I'm going to see if that checks in this equation. So I'll say 3 equals -3 plus 5 squared minus 1. -3 plus 5 is 2, squared is 4, minus 1, which equals 3, and 3 equals 3, so it checks. So once again, I've graphed this function without plugging any numbers into this equation. It's pretty powerful. What's changed now, you'll notice, is that we have a number out in front, which means there's a stretch. Not only is there a stretch, since there's a negative, there's a reflection. So watch how I notate that when I do this problem. My parent function is still x squared. My pattern is still, for the parent function, -2, -1, 0, 1, and 2. Get out 4, 1, 0, 1, 4. But now I identify my a, h, and k, and my b. My a is multiplied to the function. So this is -3, which is a stretch and a reflection. Notice my h is inside the function and it is following a negative, so my h is equal to 2. There is nothing added to the outside, so my k equals 0. And since there's no value underneath, my b is equal to 1. This means there's no horizontal stretch, but there's a vertical stretch and a reflection of -3. So what that says is it says my y values are getting bigger and reflecting. In other words, they're being multiplied by -3. I get a negative 12, negative 3, 0, negative 3, negative 12. So really what I'm graphing now from my new origin are these x's and these y's. I'm going to take and move to the right 2 and up 0. There, once again, is my new origin. And from that origin, I'm going to now graph this pattern. It reflects the x squared graph in nature, but with a stretch and a reflection due to this multiple of negative 3 to the y value, since a is a y multiplier. So I move over 1 and down, 1, 2, 3, both sides, over 2, down 12, somewhere around here. And once again, here is my parabola, and I have not plugged a single x or y value into this equation. But I always want to check. So here, once again, is a point 3, negative 3. If this point checks, I will assume that I've graphed my function correctly. So I plug a negative 3 equals negative 3 times 3 minus 2 squared. That's negative 3 times 1 squared, which is 1, and negative 3 equals negative 3. Once again, I've graphed it without plugging into that original equation. So you'll notice in this equation, I have same parent function. Once again, we're going with our x squared, which is going to have a normal pattern. Negative 2, negative 1, 0, 1, 2, 4, 1, 0, 1, 4. A in this case is on the outside. It's the multiplier. And it multiplies y. Since it's less than 1, it's going to squish, if you will. S-Q-U-I-S-H. Squish. Squish the y values. H is in the interior of the function, and it follows the subtraction. So h is equal to 2. K is usually following a plus. This is a minus, so k is equal to negative 1. So now, we know that it is squished by the y's. Y gets multiplied, since a is a y multiplier, by a positive 1/2, and thus I have 2, 1/2, 0, 1/2, 2. Right? I move over to 2. I move down 1. Put my little hash mark for my new origin. And I'm going to use this pattern now to graph x's and y's from the new origin. So if I go over 2 in the negative direction and up 2, I should get to a point. Over 2, up 2. If I go over 1, this time I only go up a half. So you'll see that this graph now is wider than our original x squared graph. And I want to make sure I did it right, so I need to check that point of 4, 1 by plugging it into the equation. Notice I haven't plugged anything into here yet. So I have 1 equals a half times 4 minus 2 quantity squared minus 1. 1's equal to 1/2 times 2 squared, which is 4, minus 1. 4 times a half is 2 minus 1. 2 minus 1 is 1, and 1 equals 1, so this checks. Let's keep moving with some more examples. So here's the first time we have this number in a denominator of the function. So this is going to be our b value, which means in this case we know we stretch horizontally. So this is going to get wider. Parent function is still x squared. Pattern still -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. In this case, inside the function, this has got to be my h value. It follows the subtraction, so h equals 5. Nothing on the outside, k equals 0. A equals 1. There's no vertical change to this as far as the stretch goes. But b in this case is now 2. And b stretches our x values, so now we're going to multiply all my x values by 2. That's giving me -4, -2, 0, 2, 4. And now we're going to graph these x and y values from our new origin. And our new origin moves over 5 because we have a horizontal translation of 5. And we aren't moving up and down. So here's my new origin once again. And my pattern says to go over 4 and up 4. Over 2, up 1 on both sides. So once again, you're going to notice this graph did get wider than our typical x squared graph. I haven't plugged into my original function at all. I'm going to do that now to check. And I'm going to find a point that works here. Here's a point 1, 4. And I'm going to make sure this checks. So 4 should equal 1 minus 5 over 2 quantity squared. That's -4 over 2 squared should equal 4. That's -2 squared, which is 4. So that checks. And again, I didn't plug into the original function. Few more, guys. Now, this is the toughest case. We notice that it's a squared function still, so we have this parent function of x squared. We have this pattern still existing of -2, -1, 0, 1, 2. Inside the function itself, I have this 6, which looks like an h value, and it is, but it has to come after the subtraction. So be it. Now this 2 is the problem. Inside our function, we can only have a coefficient of 1 in front of x, which I do right here, but this 2 is throwing me off because I need a fraction of b. So what I need to say is this 2 can't be here. Something needs to be on the bottom, but this needs to be of and by itself, and that needs to be +1. So how do I multiply by 2 but use a division? Well, if I divide by 1/2, that's equal to multiplying by 2. So I can rewrite this equation as such. And notice, now I have this b term, which is 1/2, and this h term, which is 6. So I know h is 6 with a negative type, which means it's going to move to the left, and I have a b value of 1/2, which means all my x values are going to be squished in by a multiple of 1/2. So once again, I'm going to go back 6, like so, and call that my new origin. B affects those x values. So all these x values have to be multiplied by a half. That's giving me -1, -half, 0, half, and 1. So now I'm going to graph these x and y values from this new origin. I go over -1 and up 4. I'm going to go over 1 and up 4, and then I'm going to go over a half and up 1. So you'll see that this normal x squared graph has been squished in. Now let's take a point like -5, 4, plug it in and make sure it works. And again, I haven't done anything as far as plugging into this equation. So I have 4 equals 2 times -5 plus 6 squared. 4 equals 2 times 1 quantity squared, or 2 squared, which is 4, and it checks. So that's what we've got done as far as just the graphing goes. Now, for some people, this is much harder, writing the equation of a graph with the translations and the transformations in it. We said already that all graphs look like y equals some a x minus h over b plus k. Our parent function is x squared, so right now I can do this, y equals something squared, and all I have to do is find these values. Now, when we find all the values, my recommendation is you only do one type of stretch if at all possible. So what I usually do is I worry about my a value. And I always set my b value equal to 1. I say it's only, if a graph moves outward, you can say that is a horizontal stretch, okay, or a vertical squish. And I usually go with the vertical because it's easier to solve for. So I'm always going to set my problems up this way. Now, the nice thing is, in every parabola, you're probably going to have the vertex. And that vertex, which is usually at 0, 0, has probably been translated. You'll notice this has been translated up 6. Up refers to the k value. So what I'm going to do is I'm going to substitute a 6 in for this k, and since it hasn't moved over at all, I'm going to call my h 0. So I have a, which I still don't have, x minus 0 squared plus 6 equals y. Now in order to write the equation, I need values for a, b, which I already have. We said b is equal to 1. H, which I now have, and k, which I now have. So all I'm missing is a. Well, how do I find that? The easiest way, I think, is to pick a point on the graph. For instance, 2, 2. So if y equals 2, we don't know what a is, and x equals 2, I can solve for a. So I have 2 equals a times 2 squared plus 6. So this is 4a plus 6 equals 2. -4 equals 4a, and a equals -1. If a is equal to -1, my equation should be y equals negative x minus 0, so I'm just going to say x squared, plus 6. Which makes a lot of sense because this has been reflected and moved up. Notice, if I go from 0, 0 to 1, 5, I've moved down 1 and over 1. And then I've gone down 4, but only over 2. So that's kind of like my standard pattern of over 1, up 1, over 2, up 4, but this has been reflected, thus the negative. Let's do one more and call it a day. So here's this new graph. Here are the points on the graph. Y equals x squared once again, so I have y equals a times x minus h squared plus k. I identify my vertex, which appears to be at 4, negative 5. So I'm going to plug those values in. I have y equals a x minus 4 squared minus 5. And then what I want to do is find another point on the graph. This looks like the point 5, negative 3. Now I'm going to plug that into x and y. So negative 3 equals a times 5 minus 4 squared minus 5. Therefore I have negative 3 equals a times 1 squared minus 5. This gives me negative 3 equals a minus 5. So 2 is equal to a. Therefore, y equals 2 times x minus 4 squared minus 5. And there's my equation. I know it was a long one, but needed to be done. Make sure you do your summary and connect ed problems for lesson 13. We'll see you tomorrow.